Day 69, and we're dealing with dynamic programming. I think the minimum level of difficulty any video will have is medium. So prepare yourself. It's gonna be an interesting series of videos. We have quite a few. So I think this will take at least 2 weeks of videos to cover. So let's get into it. Introduction, dynamic programming. Many computational problems are solved with a divide and conquer approach recursively. Recursion. Dun dun dun. In these problems, we see an optimal substructure, that is, the solution to a smaller problem helps us solve the bigger one. For example, the string is the string rotator or palindrome. And we can start by observing that the first and last characters match, so the string might be a palindrome. We shave off these two characters and try to answer the same question for the smaller string otato. We keep doing this until we're able to say a definite yes or no. In some of these problems that can be solved with the above approach, there are overlapping subproblems. That is, we find ourselves solving the same subproblem over and over. That's what an overlapping subproblem is. The recursive solution to the palindrome problem does not have this characteristic. Aha. But solutions to many other problems do have overlapping subproblems. An example is the recursive computation of the nth Fibonacci number. Here's a recursion tree for the solution of this problem with n equals 4. So it's Fibonacci of 4, and we can see that Fibonacci 2 is evaluated twice, here and here. Fib 1 is evaluated thrice, here, here, and here. And Fib 0 is evaluated twice, both here and here. Now, these are repeated overlapping subproblems, and we can use the dynamic programming pattern to save the result once and use it wherever the subproblem is repeated. Now, we're going to use examples over the next few videos to flesh this out, so don't feel one kind of way if you can't really see or understand what we mean by all this. This is a topic covered in various algorithm textbooks, so feel free to do some extra research on your own. I mean, ChatGPT might be good to explain further. But this is an intro video, so I'll just keep it short and sweet so we can get into the meat of things by tomorrow's video. So now in this pattern, we need to save computations, right? So we just pull the results of previous computation that we need now that we've seen before. But how do we save them? And they say there are two approaches in dynamic programming: the top-down approach with memoization and the bottom-up approach with tabulation. So for the top-down approach, we store the results of solved subproblems in an array or hash map. We use the results of these stored subproblems whenever we encounter an overlapping subproblem during the recursion. So for instance, we calculate fib2 for the first time in the left subtree of the root node, and then we store the value then, and then we simply look it up later rather than recomputing it when we need it again in the right subtree of the root node. So when we got it here, we see it here the first time we store the results, so that when we get to this point and we need it again, we just retrieve that result that we stored. And that is what memoization is about. Memo is like keeping a memo. I think it's is it Latin or Greek to remember? So that's what memoization is. And then the next one is tabulation. So, and it's bottom up. So in this one, you're not even using recursion the way you used it in the top-down approach. You're using an n-dimensional array to store the results of solved subproblems. And we use the results of these stored subproblems whenever we encounter an overlapping subproblem during the iteration of the array. So for Fibonacci, we create an array of size n plus 1, yada, yada, yada. With the ith value, we eventually hold the ith Fibonacci number. We initialize the indices 0 and 1 with values 0 and 1. First fib of 0 is 0, fib of 1 is 1, respectively. Then we compute the values for 2, 3, 4 up to n as the sum of the values of the previous two indices, because that's how you calculate Fibonacci series. The bottom-up approach on some problems requires computing two-dimensional arrays. And many times we can optimize the space complexity by using a one-dimensional array instead of this two-dimensional array. You can convert a two-dimensional array to a one-dimensional array. Now the idea is to use the same array for the previous and next iteration. But this optimized approach is a bit tricky and might not be applicable to all dynamic programming pattern problems. And these are some examples of dynamic programming issues. We're not going to look at the solution, but you might be able to see how we can we can use these two methods to find the solution. So we have two DNA structures having nucleotide bases, adenine, guanine, cytosine, and thymine. Find the length of matching maximum matching genetic codes. So this is super complex. So let's just you can look at it, you can read it in your time. We're not going to go through the solution right now, so it just seems a bit kind of out of place, I have to say. Would have preferred something more practical, and we have some more reasonable, more practical, more relatable problems down the line. I mean, the very next video. So stay tuned. Pascal's triangle, we have to return the first rows of Pascal's triangle. And they don't explain what Pascal's triangle is, but you can have a sense for what it is by looking at this. Again, not super helpful, I have to say. So how do you know if the problem matches this pattern? Yes, if you have overlapping subproblems. So we can use the result of one subproblem when solving another one. Another possibly larger subproblem. An optimal structure, that is if the final solution can be constructed from the optimal solutions to its subproblems. And know if these conditions are fulfilled. There are no overlapping subproblems, and if the optimal substructural property is violated, that is, you cannot construct the final solution from the optimal solutions to subproblems. So real world problems, many problems use a pattern, a load balancer. So finding the optimal way to handle a given workload by using servers with different workload handling capacities. Search engine. So check if white spaces can be added to a query to create valid words in case the original query does not get any hints on the web, hits on the web. So if you make a search and there's no result, oh, can we put some white spaces in there so that we actually get some results on the internet? So find all the possible queries that can be created by adding white spaces to the original query. So strategy time. So we're going to match problems to whether they use this dynamic programming pattern or some other pattern. So given a set, return the numbers of subsets whose sum equals 10. Yeah, it should be dynamic programming. Solve Sudoku puzzle. Oh, Sudoku is a backtracking problem, not a dynamic programming problem. All the ways I safely place 5 queens on a 5x5. This is an n queens problem. It's a backtracking problem, not a dynamic programming problem. Maximize your heist without robbing neighboring houses. Could be, according to them, it's dynamic programming, but even though we literally did something similar in backtracking, I believe. So I guess there's quite a bit of overlap, right? Some backtracking problems are actually seem to be dynamic programming problems. And these are the explanations if you want to pause and look into each of them. But that's that about that. Video is over. See you in the next video. Okay, we'll do some interesting problems in this series. Ciao.